if you are watching this, if you can figure out what this t-shirt actually says, because obviously it's backwards, and this gives you a little bit of a hint of how I do the videos, because everything is reversed. I'm actually on the left, but you're looking at me on the right. Do you get this t-shirt? So if you do, put a comment in the video comments, okay, and tell everybody else why I'm wearing this. It should make sense. Just read it across. And if you know a bit of chemistry, you'll understand this word, okay? This word across here, okay? Right, let's get on with the actual lesson. So, acid, base, and buffers, we're going to do neutralisation, okay? We can start off with the question straight away. So if we add a strong acid to a strong base, we're going to get an example of neutralisation. Neutralisation is where H plus will equal the amount of OH minus. So you've neutralised basically all of the OH minus and the H plus. Essentially, they're neutralising each other out and they're creating water. Okay, so we've got here neutralisation where we've got H and OH adding up together, and they're going to make this water that is here. Okay, so signs of neutralisation reactions is that you often create water. You don't always. It's an acid plus a base generally. Now, stop the video, try and make this into an ionic equation. Okay, give yourself a little bit of practice. But the ionic equation is H plus OH minus. We get rid of our spectator ions, which is Cl minus and Na plus and everything else, and we just get left with this neutralisation for neutralisation ionic equation. So let's look at this titration question. So in this titration question, and we've done a little bit of working out for you already, in the titration, 25 centimetres cubed of the aqueous sodium hydroxide has a concentration of 0.25 moles per decimetre cubed. It's neutralised by 9.2 centimetres cubed of the hydrochloric acid. It wants the pH of the acid. Okay, so that's the original acid. So what's the pH of that original acid? What's the pH of this? Now to do that, we have to get hydrogen ion concentration of the acid. The next thing we have to do is, this is a strong acid, so it's fully dissociated. Okay, so whatever the, and plus it is monobasic, which means it donates just one proton, which means that the concentration of this completely dissociated acid is the same as the concentration of the H plus ions. And we need the H plus ions to get the pH. So let's go through this calculation that we've got here. So we've got number of moles of sodium hydroxide. So the sodium hydroxide, you can work it out because you have the volume, which is 25 divided by 1,000, times by the concentration. So volume divided by concentration, and you're given the volume, and that's that there, and you're given the concentration, which means that you get this number of moles. Now the number of moles, because it's a 1-to-1 ratio here to here, the number of moles of the sodium hydroxide is equal to the number of moles of the hydrochloric acid. Now, if that is the case, we can use the number of moles to calculate the concentration of the acid, which is equal to the concentration of the H+. Okay, so let's try and do that now. So we have got the number of moles of hydrochloric acid. Remember, if we want to work out the concentration is going to be equal, and we want the concentration of the HCl. So the concentration of the HCl is going to be your, if you do the equation quickly and swap it around, okay, so you've got this equation here, so you've got volume, concentration. So I want the concentration, so I'm going to have to take the moles and divide it by the volume. So number of moles of HCl divided by the volume of HCl. Okay, now number of moles is 6.25 times 10 to the minus 3. Okay, 6.25 times 10 to the minus 3. And then the volume is over here, which is 9.2. So it's 9.2. Remember, we're doing it in decimeters. So it's 9.2 divided by 1,000. Now, if that's the case, okay, we can finish it off. We can find out that it is 0.67934, and then it is the numbers in the calculator. So we've said this very much, you don't round at any point, it's the numbers in the calculator. That is equal to our H+, because this is a fully dissociated acid, right? So that means your concentration, so your H+ concentration, okay, your H+ concentration is equal to 0.67934. Okay, so same number. So your H+ is equal to that. Now, if that is the case, let's move on to the final part. Final part is pH, and it's pH equals minus log of H plus, which tells you the pH of the original acid, which equals minus log, okay, and then that's of, again, 0.67934 dot dot dot. Okay, and there you have it, and there's your number. Let's make that 6 a bit better. Okay, and then you've got your number here, put that into the calculator, and you'll get a pH of 0.17. Okay, so your original one was 0.17, and that's your answer. Remember, to 2dP. Can't say that enough. All pHs should be to 2dP. So we have got a titration where you want to know the pH of the original acid, and that is how you do it. Enjoy. So we're now going to go through a titration curve, and you can see there's pHs down the side here, and then there's the volume of HCl added. Now, anything that's added, if it's a titration curve, is going to be added from the burette to the conical flask. That means the volume of hydrochloric acid is coming from the burette, and the alkali, 14, which is in your equation here, so sodium hydroxide, okay, that is in your conical flask in this example. But you can do it either way. If you started off with hydrochloric acid in the conical flask, it would start down here and then go up. Okay, so it depends on what you start with. But in this one, we've got the hydrochloric acid in the burette, and we've got the sodium hydroxide in the conical flask. And you can see as you go along, you can see the pH is changing very gradually as I add the hydrochloric acid, bringing the pH down until we get this vertical section. This vertical section tells you the volume of the acid used to neutralize the alkali. Okay, so this is we're finding here our neutralization point, and this can be used to do a titration calculation. We also use a pH probe. So here you just draw a line down from the vertical section, and that is your volume of acid that you add in to neutralize the sodium hydroxide. And you can use that to do titration calculations if you're given other information as well. Remember, the pH meter and probe is really to be used in your PAGs, and can be a question when they say, how do you measure the pH meter and a probe? Now, let's go into a bit more detail about this, okay, and why it actually works in this way. So first of all, it's all based on the pH calculation minus log to the base 10 of H plus. Now, I include the base 10 on this one. Sometimes I don't write the base 10, but in this I include it because it changes everything by a power of 10. So let's do an example here. Same reaction, but this time we're adding base. We've just swapped it around. We're adding base just to keep the numbers simple. So 0 to 1. Okay, needs 25 centimeters cubed of base adding. This is just an example. Because it's a log to the base 10, when we go to the next pH unit, it reduces by 10 because it's log to base 10. If we go from 2 to 3, it reduces by another 10. We go from 3 to 4, it reduces by another 10. So the volume of the base that needs adding is getting down by 10, by a power of 10, every single time until it's literally droplets will change it. And that's when you get your big vertical section. Okay, so we only need half a drop to go from 3 to 4, and another half a drop of that will then take us all the way down to pH 11. So bang, and that's where you get that big straight line. Now it's really important to think about two terms which you're going to have to go through. One is called equivalence point, and this occurs when there's an equal amount of H plus and OH minus in the flask. Equivalence point is also what you call neutralisation, so when the H plus and OH minus equal each other. And the end point is when the indicator changes colour. So you need an indicator in all of this. So your indicator is in here, and when that indicator changes colour, you've got your end point, and when you get that big vertical section, inside the big vertical section is when you get this equivalence point. Okay, but I'm going to keep calling it a vertical section because it's the easiest and simplest way to do it. Okay, so it's really, really important. So if we look at an actual graph here like this, we can see the equivalence point. Okay, the equivalence point is going to be in here. Okay, and the end point is when it changes colour. Okay, so really, really, really important. Now, when you're doing this, it'll be really important when you're choosing the indicator colour, which we'll do now. So let's talk about indicators. And indicators are just basically a weak acid that has its conjugate base. So let's just go underneath here and you can see the conjugate base is there. That will have a different colour to the actual acid itself. Okay, because it has a different colour, depending on what the equilibrium goes, you will get a colour change if you've got more of that or if you've got more of that. That's all you really need to know, not much at all. Okay, they each have a different colour and vertical sections of the differing titrations. You look at the vertical sections, and if the vertical section has the same range in terms of the colour change for the indicator, which will make sense in a second, okay, then you can choose that indicator. So if we look here, strong acid, strong base, pH 11 to 3-ish will be the vertical section. Okay, strong acid, weak base, the vertical section will be 7 to 3. Okay, and you can use methyl orange or phenolphthalein, we'll explain that in a minute. Okay, and for strong acid, weak base, you can use a methyl orange. Now for a weak acid, strong base, you tend to use phenolphthalein. Again, I will explain it in individual levels, but you have to remember these three. Okay, now here are the colour changes that you get. And we've done the boxes so that basically you know when you go below this pH you'll get red, above that pH you'll get yellow. And the same with the phenolphthalein, above the pH we've shown we'll see it will go colourless. So an acid it's colourless and an alkali it's a pinky purple. Now let's have a look at the examples to make this make sense. Strong acid added to a strong base. So there's a strong base, here's a strong acid. Okay, now all we have to do for deciding an indicator, and we'll show you the exam answer in a second, okay, is look at the vertical section and see which one of these fits in the vertical section. Now you can see that the methyl orange just about fits into that vertical section, 3.1 to 4.4. So 3.1-ish to 4.4, it's kind of just, but it's not perfect, it's almost on the bend, so I wouldn't really choose that. If we look at phenolphthalein, okay, that's colourless to pink, okay, and colourless and pink, and you've got 8.3 to 10.5. Well, that's 8.3 is around about there, 10.5, that's really in the vertical section. So for this one, I'm going to choose phenolphthalein. Okay, that's going to be my one. And that's what I mean by, is it within the vertical section range? Is the range in which it changes colour, which is that range 8.3, 10.5, in the vertical range of this titration? If we change it here, and we're looking at a different one. So we're now looking at, you've got a weak base, and adding to that weak base is a strong acid. Okay, so weak base, because it's around about 10, strong acid, it's around about 1. Okay, we look at the vertical section again. The vertical section here, and we see which one fits. Well, the 10.5 is about here, so it's all on this bend. It covers this bend. We need it to be in the vertical section. We need this range that you're given here to be in the vertical section. So 3.1 to 4.4, 3.1 to 4.4 is around, right bang in the vertical section. So we're going to use methyl orange for this. And that's what you need to be able to do. Now let's go for another one. Weak acid added to a strong base. You can see it's a strong base here. And we got the weak acid here. Okay, again, just look at the pH levels and that's how you tell. Right? Now, if that is the case, we're looking again, we're seeing where's the vertical section going to be. So the vertical section is here. 3.1 to 4.4 is, it's here, so it's nowhere near the vertical section, so we're not going to use methyl orange. Okay, and then 8.3 to 10.5, well that is right on the vertical section. So we're going to finish these with just a strong base added to the strong acid. You can see strong base starts off at 1 acid, and then so we're going to start off with the strong acid, okay, and then to the strong acid, because this is at 1, okay, you're going to add the strong base. A nice vertical section right here, okay, and you probably could use both because both of them fit, but a phenolphthalein fits definitely in this section here. So basically we would use phenolphthalein because it fits. So this is how you look at the graphs and decide which indicator you're going to do. So we're going to quickly do an exam style question on indicators, and you can say choose with a reason. Okay, so you've got to give a reason and choose which indicator you're going to do. They'll always give you questions like this around about 2 marks. So all you have to do is look at that vertical section. So let's look at that vertical section. Highlighted here, there's the vertical section. Which one of these fits? Which one of these ranges fits within this vertical section? Well, it is thymethylene, okay? So thymethylene. Now, if that is the case, what's the actual exam answer for this? You've chosen the one, so you'll get 1 mark, but what's the actual answer? It's thymethylene, so choose, you've chosen, with a reason, and the vertical section. So the range fits within the vertical section, okay? So you've got to say rapid, that pH change matches the pH range, okay? Or you could say the vertical section matches the pH range of the indicator, okay? But there's many ways of saying it, but you've got to mention the vertical section and the thymethylene. So another type of exam question that is related to this is to be able to draw on the axes what the curve would be. It's quite a simple one if you're used to doing it, so it's well worth having a go and things like that. Okay, now if you look here, you can see we've got our pH scale and we've got our volume of sodium hydroxide. So we're looking to find out how much of this sodium hydroxide is added to give us our vertical section. So we want to know where that equivalence point is, where it's going to be. And we can do it via the moles. So on the axis, sketch a pH curve for the pH changes during the addition of 50 centimetres cubed of 0.1 and 30 centimetres cubed of 0.8 of the acid. So there's our number of moles of the sodium hydroxide. And there's our number of moles. And all this is volume times concentration. So volume times concentration. So we've converted our volumes into decimeters. So 50 is 0.5. Okay, and then 30 is 0.03. And then we've times them by the concentrations. You can see here the concentrations taken straight from here. We've got our number of moles. Now we need to find out which one is in excess and which one is the limiting reactant. So the smallest number, it's a 1-to-1 ratio for sodium hydroxide and this acid. So basically, this is the limiting reagent here. So C2H5COOH, or written CH3CH2COOH, same thing. Okay, so that's the limiting reagent. The NaOH is in excess. So that basically means that the neutralisation point will be when the number of moles of the limiting reagent equals the number of moles of the sodium hydroxide. So we know the number of moles of sodium hydroxide that we are going to need for neutralisation point for this equivalence point is going to be 0.0024 moles. So 0.0024 moles. So if it's 0.0224 moles, we can rearrange this equation, number of moles equals volume times concentration, to equal volume equals. So volume equals is moles divided by volume. So moles divided by volume here is 0.0024, which is this number here, divided by the concentration of the sodium hydroxide, gives you the volume of sodium hydroxide. So then we can use that, all of that is used to draw. So first of all, before we draw it, we need to know relative shapes of these things, and they're just basically an S like this. Okay, and then we have to look and say, what are we adding what to? So addition of the sodium hydroxide to the acid. So we're going to start at the acid's pH, and it's going to come from an acid pH, and we know that's a weak acid, so we don't have to be incredibly accurate here, but somewhere around here, 4 to 6, okay, it's going to come up, that nice curve, vertical section here, and then it's going to finish, because we keep adding, the NaOH is in excess, so we're going to keep adding the NaOH, and it will go to the pH of NaOH, which is around 14. So there we have it. And so what they're looking for is this nice vertical section, and that the pHs are roughly equaling what the pHs of the alkali and the acid are. Okay, so they can do this with any acid that's strong, any acid that's weak, but they'll give you information, tell you it's a weak acid or tell you it's a strong acid and such and so forth. And remember, they only get you to deal with strong bases. And that is how you draw a curve. So we're going to look at one final question, which is potentially one of the most hardest questions that you're going to come across, and if you're unlucky to get. Okay, so this question is based upon this equation here. And the key is, when does pKa of an acid equal its pH? So if you're asked to, and we'll go through this in a further video, if you're asked to pick an acid to do a buffer of a certain pH, always pick the acid with the pKa that's closest to the pH that you want in the buffer. So if the pH of the buffer that you want is 3.55, and you've got a load of acids to make it from, and you're just looking for the pKa that is closest to 3.55, and that's the acid you choose. Now why it's generally because of this. So when does the pKa of an acid equal its pH? So let's talk you through how you do this. So basically, we've got 25 centimeters cubed of KOH, the equivalence point essentially, roughly in the middle of the vertical section, when your H plus equals your OH minus. Okay, so that means for this equation here that we have got OH minus equaling H plus, which means all of this is used up because they'll all react to make this and this conjugate base. So we only have the conjugate base. That's it. At this point, we only have the conjugate base because the same amount of moles of the KOH as the acid, so they both reacted with each other and just made this and water. Okay, so we just have the conjugate base. So if we go to this next point, which is halfway, so this is about 25 and this is about 12.5. So we've just done halfway by going 25, half of that is 12.5. And we looked at this point. Now, if that is the case, that means that there's 12.5 centimeters cubed of KOH, so it's half neutralized. So what do we mean by half neutralized? What we mean is we've added half that we need to react fully of the acid, which means we have 50% of this left. Okay, if that's the case, we have 50% of that made. And if we carried on to this point here, we just have 100% of this. We've got 50-50. Now, there's an equation called the Henderson-Hasselbalch equation. Okay, and essentially, what we can do is we can say, right, that means our moles that would be here and our moles that is here are literally the same number. Or if you do concentration here and you do concentration here, it's essentially the same number. Okay, because you've got 50% left and 50% made. Now, in the Henderson-Hasselbalch equation, which is just a combination of pH and a Ka equation, essentially, if you look here, you can see that it's got the conjugate base A minus and the weak acid there. Well, that means this is the weak acid, this is the conjugate base. We've just said they're the same number. If they're the same number, then dividing the same number into each other equals the number 1. Okay? Now, if you do maths, this is quite easy, but if you don't do maths, just follow what I'm saying. The log of 1 is equal to 0. If the log of 1 is equal to 0, that means the pH is going to equal the pKa. Okay? So that is how you use the Henderson-Hasselbalch equation to prove that the pH at half neutralization point, that's really important, this only works at half neutralization point, the pH equals the pKa. And this is an incredibly clever part of the course, and I'm very impressed if you all get it. Now, I hope you enjoyed this video, and remember, what does this mean?